Okay, welcome class to a lecture on your organic reactions. So this preliminary lecture on organic reactions will be important, especially when we go to discuss our alkanes and their different reactions. So the objectives of this lecture is divided into 5. The first one, we will be identifying and differentiating the different organic reactions based on reactants and products. The next one, we will be describing what a reaction mechanism is. The third will be differentiating a radical reaction from a polar reaction. The fourth will be differentiating an electrophile from a nucleophile. And last is how to use the curved arrows in a reaction mechanism. Okay, so to start, let us discuss the different types of organic reactions based on the reactants and products. So the first one is your addition reaction. Okay, so an addition reaction occurs when two reactants add together to form a single product with no leftover atoms. Basically, this is A plus B equals C. Okay, so you have reactant A. You have reactant A plus reactant B. You have a product C. Okay. Now, please take note, class, that when an addition reactant forms or an addition reaction forms, there is no leftover atoms, meaning when A and B combines, it only forms one product. There is no second product. Okay. Next, we have our elimination reactions. So elimination reactions is the opposite of our addition reactions. It occurs when a single reactant splits into two products. Okay, so in this element or in this compound, you have A that will be will degrade into B and C. Okay. Okay, so that is the summary of this reaction. One product becomes one reactant becomes two products. Okay, please take note that there is only one reactant in this reaction. Next, you have a substitution reaction. A substitution reaction occurs when a reactant exchanges parts to give two new products. So on the screen, you have methane plus chlorine gas. In the presence of light, will form chloromethane and hydrochloric acid. So you might be familiar with this one when we discussed our alkanes. Okay, so what happens here is two reactants will exchange their atoms. Okay, see the difference? So hydrogen went to the second reactant, to the second product, while chloride went to the first product. Okay, so the general formula for this one is A plus B equals C plus D. Okay, so they exchange their parts. Is it clear? Okay. And the last type of reaction is your rearrangement reaction. So rearrangement reaction only has one reactant. However, it just rearranges itself to form an isomeric product. It transforms into another isomer of itself. See, you have your 1-butene in the presence of a acid catalyst becomes 2-butene in this manner. Okay, so one reactant becomes another reactant, an isomeric product of itself. So let's have A1 becomes A2, since they are basically the same molecule that just rearranged itself. Okay, so moving on, let's have reaction mechanisms. So how does reactions occur? A reaction mechanism is an overall description of how a reaction occurs. A mechanism describes in detail what exactly takes place at each stage of the chemical transformation, which bonds are broken and in what order, which bonds are formed and in what order, and what the relative rates of the steps are. A complete mechanism must also account for all the reactants used and all the products formed. Okay, so what do we need to take into account when we are talking about the mechanism? So we need to state which bonds are broken, which bonds are formed, broken and where, formed where, what order. Okay, as you move on through organic chemistry, you will be encountering that the order of which bonds are broken and which bonds are formed are very important, and what the relative rates of the steps are. And finally, a complete mechanism must also account for all the reactants used and all the products formed. Meaning, if you use a certain number of molecules or a certain number of atoms, they must all be accounted for after the reaction has finished. Where did they go? Where did they come from? Should also be described. So all chemical reactions involve at least bond breaking and bond making. We have two ways that bonds can break. First, we have our electronically symmetrical way. One electron remains with each product fragment, also called a homolytic reaction. Electronically unsymmetrical way, both bonding electrons remain with one product fragment, leaving the other with a vacant orbital, also known as your heterolytic. So this is the two types of bond breaking. So on the first one, you see that when this whole compound broke, both A and B got one electron each. Clear. And the other one, this whole molecule broke, both electrons went to B instead. So what happened is A was left with an empty orbital and B has an extra electron pair, leaving A with a positive charge and B with a slightly negative charge. So this one is your symmetrical and this one is your unsymmetrical. Remember that in symmetrical, each has one electron. While for unsymmetrical, one has an electron pair. Okay, so analogous to your bond breaking, you also have two ways bonds can form. You have unsymmetrical bond making and unsymmetrical bond breaking. Bond making. So it is very analogous to the first one, in which in symmetrical bond making, each atom has an electron. They share the electrons between them to form the final product. And while in unsymmetrical bond breaking, one compound has an electron pair while the other one has a vacant orbital. And still they form the final product. Okay, so processes that involve symmetrical bond breaking and bond making are called your radical reactions. A radical, often called a free radical, is a neutral chemical species that contain an odd number of electrons and thus has a single unpaired electron in one of its orbital. So it is neutral in nature and it contains an odd number of electrons, meaning it could only be 1, 3, 5, or 7, and has a single unpaired electron on one of its orbital. So let's have an example. Let's have chlorine. Okay, so chlorine can exist in one or two forms. You have chlorine gas, which is Cl2. You also have your chlorine ion, and you have your chlorine radical. So to differentiate, chlorine gas or natural chlorine is two chlorine atoms bonded to each other. They are stable this way. That is why chlorine is found in this configuration. Chlorine ion or chloride, on the other hand, is a chlorine with complete electrons on its orbitals, thus it is having a negative charge. So naturally, chlorine has a valence of 7. When it gains an electron, it becomes an stable stable atom. That is why it is slightly negative, because of the extra negative electron. Okay, electron pair. While on the other hand, chlorine radical is simply chlorine with one extra electron. So it is not actually an extra electron, it is just a odd number of electron that is unpaired. So see the difference? Especially, you might be confused with this too. Okay, so chloride is stable because it is in the octet conformation or octet configuration. It is negative in nature and it has 8 electrons. Well, chlorine radical is unstable. It is not conforming to the octet rule, and it has no charge, meaning it is neutral, and it has 7 electrons on its shell. Okay, so chlorine gas is also stable because both of this chlorine has the octet configuration. Chloride also is stable because it has 8 electrons. Chlorine radical is the unstable one. Okay, so I hope you know the difference between a chlorine radical and a chloride ion. Okay, so the next type of reaction is your polar reaction. Polar reaction is a process that involves unsymmetrical bond making or bond breaking, and these reactions involve species that have an even number of electrons. When you compare polar reactions with your radical reactions, polar reactions has an even number of electrons, and thus they only have electron pairs in their orbitals. These reactions are much more common. And finally, a third type of reaction is your pericyclic reaction. So a pericyclic reaction is a unique type of reaction in which the intermediate state of the molecule has a cyclic geometry, and the reaction progresses in a concerted fashion, and the orbitals involved in the reaction overlap in a continuous cycle. So these are mostly involved with aromatic compounds. Okay, so let's first dive deeper into your radical reactions. So radical reactions are not as common as polar reactions, but are nevertheless important in some industrial processes and in numerous biological pathways. A radical is highly reactive because it contains an atom with an odd number of electrons, usually 7, in its valence shell. A radical can achieve a valence shell octet in several ways. Okay, so the first way is when it abstracts an atom and one bonding electron from another reactant, leaving behind a new radical. The net result is a radical substitution reaction. So look at the screen. So you have a radical. So a radical, please remember, has an unpaired electron. So it is 1 electron. What it will do is it will grab another electron from this bond, and it will attach itself to the reactant or the atom A, forming a radical plus the A atom. Okay, so what happens is this electron and this electron forms this bond. Okay. However, what happens to the other electron? This other electron will move towards B, and B will separate. That is why you have B here. That is the next radical. So it is a substitution reaction in which you yield another radical. The initial radical becomes stable by grabbing another atom to bond with, while that atom which it is originally bound to produces the next radical. Okay, so it is like stealing a bonding atom from a stable reaction, stable product. So alternatively, a radical might be able to bond with a double bond, taking one electron from a double bond and yielding a new radical. The net result is a radical addition reaction. Okay, so what happens is your radical here will grab or will be attached to this carbon atom. It will take one of the atoms in a double bond. Please remember that one bond is equal to 2 electrons. So this bond actually has 2 electrons. One electron will go to the radical, the other electron will move to the next carbon atom. So what will happen is the radical will be attached to the carbon atom and the other electron went towards this carbon over here. Okay, so it formed one product, but that product is still has a radical component. Okay, so an example of a radical reaction is our chlorination of methane to chloromethane. We discussed this in our alkanes, but we did not delve deeper into the mechanism of action. So there are 3 major steps in a radical reaction. We have initiation, propagation, and termination. So in the initiation phase, where the radical comes from, you will know how the radicals are formed. Radicals are not common in nature because they are highly reactive. Propagation is how the radical reacts to other substances, and termination is how the reaction stops. Okay, so in our reaction of chlorination of methane to chloromethane, methane, when combined with chlorine gas exposed to ultraviolet light, will form chloromethane and hydrochloric acid. So the first step is your initiation. The first step is the initiation step. Chlorine gas is irradiated by UV light, and the chlorine-chlorine bond will break to form 2 chlorine radicals. So this is a type of symmetric bond breaking, okay, in which one atom each went to the each electron went to each atom. So you have 2 chlorine radicals, okay, from this reaction. Take note, these are not chlorine ions, these are chlorine radicals. Okay, so that is the initiation step where the radical comes from. Next is the propagation step. Once produced, a reactive chlorine radical collides with methane molecule in a propagation step, abstracting hydrogen from the atom to give hydrochloric acid and a methyl radical. Okay, so chlorine is this chlorine radical will grab hydrogen together with its electron to form hydrochloric acid. The electron left between the bond between hydrogen and carbon will now move towards this carbon hydrogen 3 molecule, forming a methyl radical. So the first product is your hydrochloric acid, and the next one is a methyl radical. This methyl radical can again bond with, it can abstract chlorine from a chlorine gas configuration, and it will grab chlorine to form your chloromethane, and what is left is a chlorine radical, which is this one. Okay, so similar to the first reaction, this radical now abstracted one atom, which is chlorine, to form your chloromethane. methane. While the chlorine left becomes another chlorine radical. So in this step, it can be repeated multiple times, and this is actually your chain reaction. Finally is how the process ends. So occasionally two radicals might collide and combine to form a stable product. When that happens, the reaction cycle is broken and the chain is ended. So please take note that termination occurs when two radicals collide, meaning it could be chlorine-chlorine radicals, or methyl-methyl radicals, or chlorine radical and a methyl radical. Okay, as long as it is two radicals, it can bond to each other and it will not produce another radical. Okay, so these are the possible termination steps. When chlorine radical reacts with a chlorine radical, it forms chlorine gas. If chlorine radical reacts with a methyl radical, it becomes your chloromethane. When methyl radical reacts with another methyl radical, it forms your ethane. Okay, so those are the steps in our radical reactions. Okay, next we have our polar reactions. Polar reactions occur because of the electron attraction between positive and negative centers on functional groups in molecules. So these are caused by attractions between negative and positive centers. Most organic compounds are electrically neutral. However, they have no net charge. However, certain groups within a molecule, particularly the bonds in functional groups, are polar. If we recall our functional groups together with our lecture on polarity, you can say that one part of the functional group is slightly positive and one part of the functional group is slightly negative. So these are the polarity patterns in some functional groups. So you have your alcohol, carbonyl. Alkene is symmetrical and nonpolar. You also have your alkyl halide, carboxylic acid chlorides, amine, aldehydes, ethers, esters, thiols, ketones, nitriles, and please take note of the two final reagents. So you have a Grignard reagent with an alkyl lithium reagent. So these are unique, in which carbon now acts as the slightly negative portion. Okay, if you look back, carbon is always slightly positive. In this case, it is attached with an atom or with an element that has a much less electronegativity compared to carbon, causing it to attract the electrons. Okay, so it will be helpful if you are familiar with these patterns. However, well, you know polarity, so you can determine what part is the slightly negative portion and one part is the slightly positive portion, based on just looking at the two atoms that are bonded. Okay, so what is the relationship of polarity to the reactions? What does functional group polarity mean with respect to chemical reactivity? Because unlike charges attract, the fundamental characteristic of all polar reactions is that electron-rich sites react with electron-poor sites. Okay, so if you look at the screen, an electrophile, which is electron-poor, reacts with a nucleophile, which is electron-rich, to form a bond. Okay, so in the screen I used, or the book used, an electrophile and nucleophile as its way of describing an electron-poor and an electron-rich region. The book will be using this throughout the text. That is why you need to clarify or clearly state what is an electrophile and what is a nucleophile. Okay, so when we say a nucleophile, this is a nucleus-loving atom. It is negatively polarized and it has an electron-rich atom. Can form a bond by donating a pair of electrons to a positively polarized electron poor atom, or your electrophile. It could be neutral or positively charged. Don't worry, I summarized this in a table. An electrophile is electron-loving, positively polarized electron-poor atom. It can bond by accepting a pair of electrons from a nucleophile and can either be neutral or positively charged. So this is the summary of a nucleophile and an electrophile. Based on the property, you must know what is a nucleophile and electrophile. So what is the job of a nucleophile? Its job is to give electrons. The charge of a nucleophile can be neutral to negative. The polarity is always negatively charged, and it is named a nucleophile because it wants nuclei, so it wants to gain a positive charge. An electrophile, on the other hand, receives electrons as its main job. The charge is neutral to positive. Please take note that nucleophile and electrophiles can be can be neutral in nature. They are both candidates if they are neutral. And the polarity is positively charged. This is named an electrophile because it wants electrons. It wants a negative charge. Okay, so an example of a polar action is your reaction with hydrobromic acid to ethylene. Okay, so the reaction is an addition of an alkyne with hydrogen bromide. Okay, so the sample reaction is polar reaction known as electrophilic addition. Alkanes are positively inert because of their electrons are tied up in strong nonpolar carbon-carbon and carbon-hydrogen bond. Alkanes, however, are much more reactive because the double bonds has greater electron density than single bonds. Electrons of the pi bond are accessible to the reactants. So in short, electrons on the pi bonds can be used for reactions. Okay. So hydrobromic acid is a strong acid. It is a powerful proton donor and a electrophile. So this is the mechanism of reaction. So what happens first is carbon-carbon is relatively neutral in nature. However, due to the nature of the pi bond, a pi bond is slightly negative in nature because it is rich in electrons. Okay, a bond is rich in electrons. However, double bonds are reactive. Okay, so what it will do is it will react with hydrobromic acid. Please take note the polarity of hydrobromic acid. Bromine is an electronegative atom. Hydrogen is a relatively non-electronegative atom. So this one, hydrogen, is slightly positive and bromine is slightly negative. So the tendency is hydrogen is slightly positive, bromine is slightly negative due to polarity of their difference in electronegativity. So this is negative, this is positive. These two will now react with each other. Okay, as we move on, and the bond between hydrobromic acid is broken, and bromine will take both of the electrons, leaving you with bromine, an ion. Okay, so moving down, this bond accepted hydrogen, and this is where hydrogen is now. This is where hydrogen went. Okay, however, it leaves the other carbon atom slightly positive. It is slightly positive because the electrons used went to one carbon atom and one carbon was left with a lacking electron pair. So what will happen is the bromine left from the first step will now move towards the carbocation. Since bromine is negatively charged and a carbocation is positively charged, they will now react with each other, leaving you with the final product. Both bromine and hydrogen are both reacted with the alkene, forming bromoethane. Okay, if you want to repeat the explanation, I suggest you slightly move back in the video. Okay, finally we have using curved arrows in polar reaction mechanisms. So the first rule is electrons move from a nucleophilic source, a nucleophile, to an electrophile. So a nucleophilic source must have an electron pair available, usually either in a lone pair or in a multiple bond. Okay, take note, lone pair, like in the cases of oxygen and nitrogen. Also in a carbo-anion, pwede rin po, carbo-anion. Or in a multiple bond. You can also get electrons from a multiple bond. The electrophilic sink must be able to accept an electron pair, usually because it is positively charged or positively polarized in a functional group. Okay, it could be positively charged in the case of a carbocation, or it could be positively charged from a polarization of a functional group. For example, all these carbons here are all positively polarized because they are attached with an electronegative atom, particularly halogen, oxygen, or an oxygen as well. Okay, so a nucleophile can attach to a positive carbon atom or in a carbocation. It could also attach to a slightly positively charged carbon, and what will happen is this bond will break and move towards the electronegative atom, which is a halogen. It could also attach to hydrogen in this case because it is slightly negative when paired with oxygen, and this bond will break and it will move towards your oxygen, which is a electronegative atom. Or it could attach itself to a carbon in this situation. A nucleophile can bond with carbon here because it is slightly positive and oxygen is slightly negative, and this bond will move towards your oxygen. Second rule, the nucleophile can either be negatively charged or neutral. If the nucleophile is negatively charged, the atom that gives away an electron pair becomes neutral. So take for example, we have our molecule here. Okay, so this oxygen is negatively charged. As you can see, it has an extra pair of electrons. That is why it is negatively charged. So in this case, again, hydrogen is slightly positive, bromine is slightly negative. So this negative portion of the molecule can grab hydrogen, forming your ethanol here. Okay, so this oxygen grabbed hydrogen to form an alcohol group. When this bond broke, the electron pair moved towards your bromine. So the final products are ethanol, methanol, and your bromine anion. Okay, so since it is already negatively charged, when it grabs when it grabs a positively charged atom, it becomes neutral. Okay, so negative plus positive, you have neutral. Okay, however, if the nucleophile is neutral, the atom that gives away an electron pair acquires a positive charge. Take for example this one. Okay, ethylene is neutral in nature. However, it has a double bond which is negative in nature. It can grab hydrogen because again, hydrogen is positively charged, bromine is negatively charged because of the difference in electronegativity. When it grabs hydrogen, when it grabs hydrogen, this one will form. Okay, and bromine, again, when this bond breaks, the electrons will move towards bromine and form a bromide bromide ion. Okay, so what happened to this structure? This structure now becomes slightly positive. Okay, so neutral plus positive, you have positively charged. Rule 3. An electrophile can either be positively charged or neutral. If the electrophile is positively charged, the atom bearing that charge becomes neutral after accepting an electron pair. Okay, so we are now talking about electrophiles. Okay, so again, in this reaction, ethylene is neutral. However, this portion is negative. It reacts with your hydronium ion. What it will do is all of these hydrogens are actually slightly positive. Okay, oxygen is slightly negative because of its electronegativity. Okay, please take note that it is hydronium ion. The whole molecule is slightly charged because oxygen can only bond up to 2. If it bonds to 3, it gains a slight positive charge. Okay, so this double bond here will grab hydrogen, and this bond that broke will move towards oxygen, giving oxygen another electron pair. So what happened to hydronium when it lost a hydrogen? It became water, it became neutral. Okay, we are talking about electrophiles, those that want electrons. Okay, so from positive, it gained electrons, it became neutral. The opposite is again, the next one is true. If the electrophile is neutral, the atom that ultimately accepts the electron pair acquires a negative charge. For this to happen, the negative charge must be stabilized on an electronegative ion or atom such as oxygen, nitrogen, or a halogen. Okay, take for example, this again, ethylene is neutral. However, it has a slight positive charge and a slight negative charge on the middle. It will grab again hydrogen. This bond will break and move towards bromine. Please take note that in this compound, they are neutral. Okay, this has no net charge. No net charge. Hydrobromic acid has no net charge. However, since bromine was the one to accept the electron, it now becomes negatively charged. Okay, so that is the last rule. The last rule actually is very simple. The octet rule must be followed. That is why carbon cannot bond up to 5. Nitrogen cannot bond up to 5. Okay, so the octet rule must be followed. Okay, so that will be all for this video. If you have any concerns or which parts needs explaining in our native tongue, please do leave a comment in the comment section, or please inform me. Okay, thank you for listening, and this will be the lecture for our chemical reactions.